Let's explore the quick display for an analog input, valve and a pump. Here is the quick display for the analog input. Here is a quick display for a valve. And here is the quick display for a pump. The quick display shows key status information, and if you have the permission to do so and the object is in the right mode, it also allows you to control the device. For these three quick displays, we can see the current status information and their tag names. For the analog input, we can see the current value of the analog, its engineering units, and we can also see a trend of what that value has done over the last few minutes. For the valve, we can see that it's currently open and that it's in loopback test mode. And for the pump, we can see that it's running forward. The buttons on the quick faceplates have tooltips enabling the user to quickly see what the buttons do. Here's an example of some of the tooltips for these buttons. Now let's look at the full faceplate for the same three objects. Here is the full faceplate for our analog input. Here is the full faceplate for our valve. And here is the full faceplate for our pump. The philosophy of the design for the full faceplates is that there is a tab for each logged in role of a user. So as an operator, I'll find most of what I need on the home tab that we're currently displaying. If I was a higher level maintenance user, I would find most of what I need on the maintenance tab, where I can do things such as bypass interlocks, bypass permissives, enable simulation of analog values or input switches. On the Diagnostics tab, I will find the list of all the things that can prevent me from operating the device. So here for the valve, I can see that I may not be able to open the valve because there's an interlock present or there's an I/O fault. The next tab that we have on the faceplates is the Alarms tab, where all the available alarms are shown and the ones that are currently active are also displayed. Finally, we have the help buttons, which bring up help for each of our objects. Now let's look at the substitute feature that's built into the library as standard. Let's say that our analog input has failed at the top of our feed drum here, and we need to simulate a value to allow us to complete our process production run. I can do that by bringing up the full faceplate and going to the Maintenance tab. Because of security, currently as a logged in operator, I don't have the ability to substitute the analog input. So I need to log in as a higher level user. Let's log in as a plant maintainer. And now I've logged in as that user, I now have the ability to decide whether I want to use the real analog input being measured from the field, or if I wish to substitute. So let's go ahead and substitute the value here for this analog input. You'll notice that I'm asked to confirm that I want to do this. Once I've selected yes, I can then select and enter in a substitute value. So I can now put in a suitable value that gets my process going. There's no need to open up the engineering tools for our controller and go online and apply any forces in the code. I can do everything that I need to do from the HMI. Now, if I'm an operator and I come to the HMI, I can notice straight away from looking at this graphic that there's something not normal with the analog input. You can see here that a question mark is shown to show that it's being substituted, and there's also a little spanner symbol to say that something's not quite normal. So, by clicking on this HMI symbol, I can bring up the full faceplate and I can see that that spanner symbol is shown on the maintenance tab. This is showing me the area of the faceplate where something is not normal. And then on the maintenance tab, I can see that this spanner is highlighted against the substitute switch. So this is showing me here that the value is currently being substituted, and this is not a normal situation. I can remove the substitution by selecting the switch. And when I do that, the maintenance symbol is removed. We call this the breadcrumb trail, and it brings you to the location on this faceplate where something is not normal. In another example, let's say that the limit switch for our valve has broken, and we need to again simulate the limit switch to allow our process to continue and complete. Again, I can do that from the faceplate. By bringing up the full faceplate for our valve, I can go into the maintenance tab, and I can decide whether the valve is using the actual limit switches or whether to simulate. Again, by logging on with suitable permissions, I can then select to say I would like to simulate the closed limit switch in this example. And now the limit switch is not being actually used for determining if the valve is closed, it's simulating that limit switch. Again, the maintenance symbol is being displayed to show that something is not normal. It's being showed on this part of the faceplate, and it's being showed on exactly where the non-normal situation is. The fact that we're not using the actual closed limit switch for failure checking, we're simulating it. I can remedy the situation again by selecting this box to use the actual limit switch value, and the maintenance symbol is removed. In our final example, let's show an example of both overriding a device and using the diagnostic capabilities that are built into the library to determine why a device is not running. In our feed drum at the moment, the pump is running and the valve is open. But let's say there's a reason that I need to close this valve. The first thing I do is I bring up the full faceplate. From the faceplate at the moment, I cannot close this valve because the device is being controlled and owned by the controller. But using standard features in the library, I can override this. The first thing I need to do is put the device into maintenance so that I can override its current commanded state. So from this faceplate, I will request maintenance control. The device is now in maintenance, and that now means from the main faceplate I have the ability to command the valve to close. Now that we've commanded the valve to close, we can see that the pump has stopped. Now, as an operator, when I come along to this graphic, I can see that the pump is stopped, but it may not be immediately obvious as to why. The standard features in the library are now to determine what's going on. I can bring up the faceplate for the pump, and immediately I can see that there's an interlock trip present on this pump that's tripped the pump stops and is preventing it from running. But what is that interlock? Well, from this faceplate I can bring up the interlock faceplate, which shows me the interlocks that are active for the pump, and now I can see that the valve not open interlock is active. From this interlock faceplate I can then link directly to the causing device for these interlocks. So by clicking on the valve not open interlock, I can bring up the faceplate for the valve that's causing that interlock. And if I clicked on the high pressure interlock, I'd bring up the analog input that causes the high pressure interlock. At the moment, the valve not open interlock is present, so I need to remove that, and I need to get the valve open to start my pump. The most quickest way of doing this is to put this valve back into program mode by removing our maintenance override. So I bring up this faceplate again, and I release the maintenance request. As soon as I do that, the device goes back into program mode, and our controller opens the valve. I can close that faceplate now. Because the interlock is not latched, as soon as that valve opens, then the pump starts again. So I can close my interlock faceplate. I can see now that my pump is running, and from the main faceplate I can see that there was an interlock trip in the past, which I can then acknowledge to remove that interlock alarm, and everything's back to normal. In this video, we're going to look at the statistic objects that are available for both motor objects and 2-position and 3-position valve objects in the library of process objects. Let's first look at the motor statistics object. First, I'm going to open up the motor faceplate, and then I'm going to go into the maintenance section of that faceplate so that I can then access the statistics for this motor. Here we have the statistics for the motor, and from the faceplate you can see the current amount of running hours that motor has been running, as well as the maximum continuous running time for any given run of a motor, the total accumulated running time, and the number of start attempts for that motor. Now let's look at the statistics object for a valve object. This is available for both a 2-position valve and a 3-position valve. Firstly, I'm going to go into the faceplate for that valve, and then again I'm going to go into the maintenance tab, and from here I can then access the statistics information for that valve. For a valve object, you can see that the statistics object collects the number of times that valve has been moved from open to closed, or from closed to open, the number of times that may have failed, the number of times that has been a slow move from one position to another. So this is basically where that move has taken longer than a configured value. You can also see that it generates statistics for the amount of time that it's been closed, the amount of time it's taken to close, the amount of time it's been open, and the amount of time that it's taken to open.